Hey guys, welcome to another lesson. It's been a while since I did the last video. It's been Christmas and the like, so I took a break. Now I'm back. So last time we did a video was on differential equations, and we started applying differential equations to logistical growth, right? So that was the one where, the context is it's a really good type of question to use with regard to COVID, in terms of the COVID context, where you have a virus that sort of infects a population and then sort of stops infecting once the population sort of gets all infected and the growth of the infection dies down. So that was the last lesson. If you haven't already done so, view that lesson. Use it to your benefit, because I suspect it would be quite a good question to ask in this year's trials, contextually speaking. So today we continue on with the application of differential equations topic. So a very common, like I've looked through the New South Wales past papers for the last 2020, so the last 2 years, since 2020 and then 2021. So there's been 2 years of new syllabus exams, where the differential equations topic, as some of you know, has only been introduced as part of the new syllabus. One of the other context questions or applications of differential equations is to apply differential equations to mixtures and solutions, right? So today I'll show you the theory that we need to do for it, and I'll show you the two sort of different types of questions that you commonly see. From all the ones that I've seen, if you sort of understand this theory, you should be able to apply it to all of them, right? So mixtures and solutions. Also, before we begin, if you haven't already done so, please subscribe to the channel, give us a like. It helps with the algorithm search, and also it gets the word out there, right? So, all these videos are free for you to use. I'm not here to sort of try to rope you in and then on-sell you anything. It's just, I thought I'd give some knowledge, give some knowledge out to the public. So here we go. So mixtures and solutions, what normally happens is they give you some sort of container or a tank, or some sort of holder of volume or liquids, and they tell you this volume either is filled to the brim or partially filled with some sort of volume. Now, what they want to talk about in this context is we're going to put something in there that's a solute, like salt is a really good example, and we're going to make this water salty, right? Over time, right, if we're pumping in water and we're sort of releasing water out, the concentration of solute or salt will change, right? So contextually, they basically have an in valve of some sort, or some sort of thing, up tap that pumps in a solution. Now, I want to define for you, or I want to introduce two variables. One's a letter C, and let's say because it's going inwards, let's go C subscript in, and then R subscript in as well. Now I'll define it here right now. So C represents the concentration. Spelled that wrong. Concentration of solute, right? I'll use solutes. In most contexts, is salt, right? Concentration of solute at, or just go concentration of solute. I was going to say at time t, not required yet. R is then the flow. Maybe I'll call it rate of flow, right? Rate of flow in and out, right? So what's important is there's two inputs in, and then there'll be two outputs out, right? So this container or tank has an in valve and an out valve, or some sort of tap in and a release out. So the inputs, generally speaking, are C of out and R of out, right? Now, what's really important for you to sort of appreciate that is that at any point at time t, right, I'm going to define three things, and the three things are important. One, you're going to have in this mixture some sort of mass of solute, right? So let's say this is the mass of the salt or of solute, right? And then you're going to have some sort of volume of water. Now, and then what, it sort of makes sense, right? That if I have like, let's say 5 grams of salt, 100 grams of water, then the concentration, yeah, can be calculated by taking one on the other. So concentration of solute, right, can be calculated as just MT divided by VT. Now, that's going to come to be more important later, but contextually, this is the question, right? Over time, you can imagine what's going to happen. We have a liquid getting pumped in that has a certain concentration of salt. Can be salt. Let's say, as a demonstration, you're pumping in water that is saltier than the current liquid here, and you're releasing water thereafter, right? Over time, you would expect that the water inside the tank, if you're pumping in saltier water, it's going to get more and more saltier, right, over time. Yeah. So there's going to be some sort of interaction between what you're pumping in, right, mixes with the current level of concentration, and then you're going to release some as well. Yeah. All right. Now, if that's a good context for this question, let's play with now the formulas and the types of questions that you'll see. So let me see how much space. Oh, got heaps of space. Right. I'm going to give you 2 key points. Right. Let's say 2 key points. Let's go point A. Now, this formula is key, right? So at the end of the day, all questions that I've seen so far deals with, they want to know what is the rate of change of the mass of the solute over time, right? In other words, they want dm dt, right? That's really the key part, because you can imagine once we do differential equations, part 1 is always a differential equation. This is the one they want, right? dm dt, change in mass over time. And then part B might be to use then your integration skills with the differential topic to get M as a subject, and then solve once they give you an input for it, right? So the way I'm going to describe this now, this might be completely different to the way school does it, completely different to the textbooks. It makes sense to me, so here it is for you, right? The change in the solute over time. The way I sort of see it is, if I'm pumping in something and I'm releasing something, then the change in the system over time would be the change in the solute over time going in minus the change in the solute over time going out. All right, that makes sense, right? Because whatever the system is, it can only change with whatever you pump in, less whatever you pump out, right? That makes absolute sense. Yep. Now, let's explore, because that right now isn't very useful. Let's make that into a useful expression that uses, can I just be absolutely clear, right? 1, 2, 3, right? These 3 guys in almost all questions that I've seen, I say almost all questions I've seen, but I'm not guaranteeing that's always the case. They're always given and they're always constant. This guy, right? This guy here is going to be the only variable, right? I'll talk about it in a sec. Now, how do we link this blue expression with the pink inputs? This is how I'm going to do it, right? Can you see I'm going to split this derivative expression to make it look like this. So I'm still going to go something in minus something out. But what's important is that by splitting this into dm dt, let's create 2 of them, right? I'm going to introduce in here dv and dv there, right? What you'll find, we're going to do it to both sides before I sort of give away the punchline. Introduce dv. I mean, I can do that, right? Mathematically, because dv's cancel out. What you're going to find is that this guy, what is that? That's a change in mass of the solute over with the volume, right? At any instantaneous point, this guy is your concentration, right? Because that's like mass over volume, right? This guy is the concentration of in. Multiply that with this guy, the change in volume over time. That is the pure definition of the rate of flow, right? This is a rate of flow. So all of a sudden, in the question here, you're going to replace both of these guys here. These guys are going to be coded or given to you as inputs, right? As hard-coded inputs. And then minus, same deal here. I'm going to replace this and this with concentration out times rate of flow out. Yeah. And once you have this as your dm dt, this is powerful, right? This is going to help you solve all questions going forwards. So from the blue, that makes sense. The pink is what we're going to use. And just to be absolutely clear here, absolutely clear. 1, 2, 3. These three guys, in all the questions I've seen, are usually constants. Yeah, given in question. So you can see, if they want me to find dm dt as an expression, I'm just going to sub in those three numbers immediately. Now, that leaves me with one to do, right? This guy. Yeah, what is the concentration out, right? The concentration out at any point in time. Now, I know it's dm dv, but instantaneously, right? This is the concentration of out. It sort of makes sense that the concentration of out is equal to the concentration, is equal to the concentration of the tank at any point in time, because you're basically releasing whatever's in the tank at that time. And we know that the concentration in the tank at that time is equal to mt on vt up there, right? Mt on vt. This is the game, right? So at any point in time, this green expression is going to be the only thing in my differential equation that is a function of m. So just to be clear here, C out is a function of m. Yeah, and I'll put in brackets and t. Maybe, right? And that maybe is going to lead me to my second point, because sometimes that expression for t is what makes it difficult. Because let's be honest, what am I trying to say here? You got a differential equation with 3 black circles, 3 black inputs. They're given in the question. They're constant. They're done. The only thing that can change and make it difficult is that green circle there. And that green circle is a function of m. If it's a strictly function of m, right, where v is constant, life is good, right? That's really easy. However, right, let's explore this concept of v. Right, so can I just make my life a little bit easier? I'm just going to move. Let's see if this works, right? I'm going to move this guy. Ah, perfect. It does work. It does fit. Move him up here, because then I can zoom in and have the formulas upstairs to continue the description. So let's go part B, right? Now, part B, I want to explore this VT. Because if V was constant, life is easy, right? The concentration of out is strictly a function of m, right? The differential equation is very easy to integrate. However, it's not always the case. Not always the case. So check this out. So once again, we know, strictly speaking, dv dt would equal to, right? dv dt in, and this is the flow, right? This is the flow minus dv dt out. Yeah? Yep, let me put a blue box around this. So that blue box makes a lot of sense, right? It's obvious, right? Yeah, so the rate of flow of the thing depends on what you're pumping in, what you're pumping out. So for example, right? For example, if you're pumping in liquid, forget about concentration, nothing to do with, if you're pumping in liquid at 3 liters a second and you're pumping out liquid at 2 liters a second, then you would expect the tank to have to grow by 1 liter a second, right? Because 3 in, 2 out, grow at 1 liter a second. That's important because your volume increases at 1 liter a second. That's what this statement's saying. The change in volume over time depends on the flow in, less the flow out, right? Now, this is key. So, and relating this to our pink inputs, right? Upstairs, this guy was R in, this guy was R out, right? That's important because let's look through it, look at it through those lenses, right? Where? Right? Let me put a pink box around this because this is important. Yeah, because that relates to our inputs. Now, let's deal with 2 scenarios, right? if the R in, if the rate that I'm pumping water in equals to the rate that I'm pumping water out, right? This is a simple, straightforward case. In fact, most cases look like this, right? So if I'm pumping in water at 2 liters a second, pumping out water at 2 liters a second, then what I know, right? The volume of water in the tank doesn't change, right? 2 in, 2 out, the volume stays the same, just the concentration changes, right? If this is the case, what am I trying to say? The volume over time is constant. It's fixed, right? It's a number. Now, it's the second case, right? If R in doesn't equal to R out. So for example, if I'm pumping in at 3 liters per second, pumping out at 2 liters per second, then over time, the volume of liquid inside the tank would change. Yeah, that's a more complicated case. So VT. Now, if we pretend that R in and R out were constant, then when we do you can prove, right, that this guy would be, when you integrate it, becomes like a linear function of V0 plus R in minus R out times time, right? Now, intuitively, what that means is that the volume of water inside a tank starts with some sort of initial volume. And if I'm pumping in 3, pumping out 2, the difference is 1. This bracket is 1. Over every second that ticks over, I'm going to increase by a liter, right? So that box there, that makes absolute sense. Now, guys, that's the formula set that I'm going to use to do the questions. Can I just say, the 2 past papers I'm going to do now basically has these 2 scenarios. The first one is this one. The second one is this one. Right? I just want to show you and demonstrate to you that everything sort of relates to this pink box here to start with. And that pink box only changes, right? The only thing that changes there is the expression for VT, where case number 1, case number 2, they're the 2 variations that are super common. So let's explore this, right? Let's explore this. Now, there's a lot of words here, so, let's just skip to the chase, right? And just highlight the things that are key. Yeah, let's highlight the things that are key. So from Norman Hurst Boys, Larshi Strauss. Okay? Saltwater fish tank contains 250 liters, 250 liters of water or liquid, right? Now, just to be clear, what is that, right? So it contains that is initial volume. So V0 is 250, right? Liters. Yeah? To keep the water clean, a pump draws out 15 liters per. Now, can you see, right? There's our first pink thing, right? Now, what is that out of all the ones that I gave you? That is a flow, right? That's the rate that it comes out, right? It's 15. Yeah? What else do we have? To keep the amount of liquid in the tank constant, 15 liters of saline solution, right? Where the salinity of that is pumped in. Now, 2 things are given there. One, that tells you what the flow is in, right? So this guy is Q in. Sorry, let me see if I can fit this in. So Q in is 15. Not only that, they give you that there is a different salinity, right, or different concentration that is pumped in. This is C in. Does that make sense? Now, can you see? They give you those. They don't give you C out, because I know that C out is just the concentration of the tank. They don't give it to you because it's not constant. It's the only thing that is a variable, right, and a function of either M or M and T, depending on the flow. Now, in this case, what's really important, can you see? The rate of out is the same as the rate of in. So I use Q, that is R, right? Yeah, I used Q in my previous formula. I've turned to R. R makes sense because R, rate of flow, makes sense. Guys, they're equal, which means the volume of the tank doesn't change. The water in the tank doesn't change. Case number 1, yeah? All right, let's see. Assuming self-dissolves, okay, cool. Now, in this case, they're telling you, yeah, I use the letter M, they're using the letter Q, same thing. Right. Let Q be the amount of dissolved salt in the fish tank after that. The tank contains, they also give you this, right? Contains that many grams of salt. Now, why are they giving you this? Most likely for purpose of part 2, when I start integrating, right? So this is the initial So I'll use Q. So this is Q0, right? Q0 equals to 8070. It's probably going to be useful for integration later. Yeah? So let's see. Prove that. We'll do it. We'll do this, right? I need to prove this. That expression there, QT, that's like QM in my formula. Over that, yep, easy. The only thing that has is function there is Q, right? Before I had M, pretty easy. And then hence solve, right? So then I need to integrate. Okay? So let's do this. So part one. Now I know, right? I know before I use the formula dm over dt equals 2, right? In minus out, so it would be C in times R in minus C out minus R out, right? That is key. Now, what I'm going to do sneakily is to replace the M there with Q, right? Because that's what it is in this case. And then sub in. So I know that the concentration of in is equal to 32.4. I know that the rate of flow in is 15. I know the rate of, oh, sorry, that should be a times, my apologies. Rate of, that's 15 as well. And this guy is missing. Yeah, this guy's missing. This was the green one that I had before. But I know that I'm going to define that concentration of out to be the same as the concentration over time, which is always going to be whatever the mass is divided by the volume of at time, right? Now, guys, first thing is the concentrate. So the mass is now using the letter Q, right? You don't need to write it as QT, yeah, because we're just using it as a variable. So Q is a variable over time, all over. Now I know the volume is constant, right? The volume is constant over time, so it's always going to be 250 liters. That never changes, right? Does that make sense? The volume doesn't change. The function of VT is 250, right? Doesn't change. So if I plug all this in, I'm hoping that by simplifying, it just gives me my answer, right? That's why it's worth 1 mark. So therefore QT, so dQ over dt equals to 32.4 times 15 minus Q on 250 times 15. Guys, I'm hoping, can you demonstrate to yourself that is 486 minus 15Q on 250, which 5 there, that's 50, and that's 3, right? And then common denominator, look, I'm not even gonna use a calculator. This guy, 2, I'm just copying the question here. Let's be amazing and just pretend that we got that right. Not pretend, I know it's right. You can do it. You can prove it to yourself on the calculator. Done. Yeah. So that's part A, pretty simple. Now, once you get part A, if that makes sense, this is exactly the same as last week and the week before, where if we're trying to solve a differential equation given that, then we just do what we used to do, right? So let me go. Sorry, that's part I. Oops. Part I, and then part 2I. Guys, start with the differential equation that we've been given, yeah, or proven. And then I'm just gonna integrate that with by putting the letters of Q to the same side, and dt, I'll put it with the 50 on here. So I'm just gonna cross multiply that. So bring this guy down, bring the dt up, and you get 1 on 24300 minus 3q dq 1 on 50 dt. Guys, integrate both sides. Yeah. Now I know this is ln, but it's because I need the derivative of the bottom on top, so times that by -3, and then times it by -1/3 to cancel it out. And now it's integrable, so it becomes -1/3 ln 240 24,300 minus 3q equals to t on 50 plus a constant. Now, this is where I sub in the constant. I've got the initial mass as well. So let's just sub it in now. Just makes life a bit easier. So when t equals 0, was my constant? My constant was 8070, right, for Q, 8070. Right, so if I sub that in, let's see, so T0, then constant equals 2. I need a calculator for this, guys. 243, let's see, 24300 minus 3 times 8070, 90. Nice. That's just negative 1/3 ln 90. Is that right? And then I sub it in, right? So therefore, negative 1/3 ln. Yeah. So what am I trying to do here? So I'm just subbing this guy into the constant to remove it. 24300 minus 3q equals to t on 50 minus 1/3 ln 90. Now, if you want to get a nice expression, combine your logs, etc. What am I trying to do, by the way? I'm just freestyling here. Hence solve. Okay, they just want the expression. Easy. So they do want me to make Q the subject, right? That's my aim. So sometimes they're like, you know, I don't even need to make Q the subject. They just want me to sub it in and solve it. So in this question, how much space I have? Yep, perfect. That's enough. Let's just make Q the subject. You're going to get some sort of exponential equation. So you know what I'm going to do? Let's combine it, right? Let's put the, you know what? Yep, let's move this guy over here, right? And factorize the negative 1/3 out, so it'll be negative 1/3. This guy minus this guy, so then combining your ln to 90 comes downstairs, right? Using your log laws, equals a t on 50. Yes, sorry, I wrote that poorly. Now, I'm going to do a few steps as well, right? So times the negative 1/3 up, so it becomes negative 3t on 50, exponential both sides, times the 90 up, right? Actually, you know, I'll do it in a few steps. So I'm going to get rid of that exponential. So it becomes 24300 minus 3q over 90. Exponential both sides becomes e minus 3t on 50. Hopefully you guys follow that. There's a few steps on there. And I'm just going to finish it off. I'm going to make q the subject, times 90, switch it around, divide by 3. Divide by 3, yeah. Therefore, q equals to, actually, let me do 3q equals to, right? So times 90 up, switch it around. 3q equals to 24300 minus 90e minus 3t on 50. Look at that. Just finished where my logo is. Divide by 3, 8100 minus 30e minus 3t on 50. Beautiful. Guys. Now, if they were nice, they would have given you another mark by subbing in t, find the value of q. They haven't. There it is. 3 marks, right? Very hard question because it's new, right? And it's not very well structured. Mixtures, solutions, very common question now. I've seen it a few times. So it's not like it's like a random context question that you see one in every, you know, once a year across 20 schools. I've seen this 3, 4, 5 times last year, 3, 4, 5 times this year. So, you know, practice it. Now, I'll give you one more question, right? One more question, past paper from James Roos, where what happens is the flow in is different to the flow out. This one, they're equal, they're both 15. When the flow changes, you have to make the concentration denominator of a volume, you have to express it in terms of T, right? Just makes life a little bit more difficult when we integrate, but not too bad. Let's have a look at this, right? So you can see contextually, same thing, a tank, salt water. Now, let's once again highlight the things we know, right? So let's see. Consistent initially of 20 kilograms of salt. So that looks to be initial. Now, what letter they're using Q as well. So that is Q0 is 20 kilograms, right? Dissolves into 10 liters of water. Now that's once again an initial input, right? Initially, there is 10 liters of water, yeah? And that's kilograms. Does that make sense so far, right? Nothing pink is given yet, yeah? Now, the pink stuff. Fresh water. Fresh water is pumped in. Fresh water implies no salt. No salt implies concentration 0, right? Fresh water is pumped in at 3 liters a minute, yeah? So, and I'll underline fresh, so highlight fresh. So what that is, guys, that is the rate in. That's 3 liters per minute. But what the word fresh means that concentration in is 0. That's important, right? And then the solution is mixed, right, by stirring and then flowing out at a different rate, right? Q out. No, not Q. I keep saying Q. Change it to R. R, I said out. Put in. Out is 2. Yeah. Sorry, I should say out. 2 liters per minute. Yeah, as shown in the diagram. But just wonder how I keep doing the pink because it relates to the formula as key inputs, right? Oh, sorry, like given inputs. Yeah. All right, let's see. Question: show that Q satisfies that, and then solve, right? And not only solve in one given after 5 minutes. Here you go. This one here, solve and then find. It's a 2-mark, so 2-parter, which is why it's 3 marks. So let's see. This one here, just be clear. They want you to find Q when t equals 5. So let's make sure we remember to do that, right? Not only do we have to find the expression, we then need to get that extra mark by solving it. Now, 2, 3 marks feels about right, but the question had 1 and 2. I think the first one sort of did a bit of was a bit unfair because I think part 1 was worth probably 2 marks, I'd say. But here we go. All right, what do we always start with? I always asked you to go this on t equals to C in, concentration in, times the rate that it gets pumped in, minus C out, minus the rate that it gets pumped out. In this case, replace the M with a Q, but that still becomes your starting premise, right? And like I said before, C in, R in are known. This guy is 0. So I don't care what R in is, but in this case it's 3. Okay, I did it again, didn't I? I keep saying times, but I keep thinking time, but I keep putting minus. And R out is 2. Now it's C out, right? That is interesting. So I know C out, the rate, sorry, the concentration that comes out is basically equal to the rate. The concentration that comes out is equal to the concentration of the system. So that's equal to CT. And I know that CT is always whatever mass is inside there over the volume inside there. Now, the difference between this one and the last one is that in this one, the expression for the volume isn't constant, right? It's actually linear. And I said to you before that VT equals to V0 plus, right, whatever rate we pump in minus whatever rate we pump out times time. Yeah, that is crucial. So in this case, VT equals to, now what was our initial volume? 10, right? 10 liters. Plus, the rate that I'm pumping in is 3. The rate that I'm pumping out is 2T. Therefore, VT as a linear expression is equal to 10 plus T, right? That is what we're going to use for downstairs. And M on the top just gets replaced. Yeah, gets replaced with the letter Q. Yeah, let's sub that in. This is what we're going to get. So therefore, my system for dq on a differential equation is equal to, that's gone, that's 0, right? Negative, because it's only flowing out. Negative of Q on 10 plus T. Yeah. Oh, sorry, so Q, I've got to times it by 2, so maybe I'll do that times 2, and then you can see that looks exactly the same as that. So I always copy the question that the solution they're asking me to prove. So minus 2Q on, I'll even put it in bracket there, not that it matters. Yeah, guys, 2 marks. But can you see, no matter if it if the flow changes between, like in this case, 3 versus 2, or it's the same like in the last question, if you start with this pink expression and then be flexible with the green expression here to get volume expression in this case, you're done, right? They all look like that. Well, all the ones I've seen, they all look like that. Start there. All right. I don't think, I don't think I'll fit it in here. I'm just going to copy this, remove this, remove this, remove this. I'm going to start here anyway, so I'll keep that. All right, guys. So then it just becomes a pure differential integration question right now. Let's go there. I'll zoom in a bit more. Let's do this, right? So what do I want? Now in this case, dq, yeah, 1 on t, that's an expression for t, so I'm just going to cross multiply. You know what? I'm going to leave the 2 there. Yeah? I'm just going to take the q over. Just makes it very clear. It makes it a cleaner thing to make the subject later, right? So I'll leave the q there. I'll leave the -2 there. So then, so I'll just bring the q down and I'll bring the dt up. So it becomes like 1 on q dq equals to negative, I'll factorize the 2 out like this, 1 on 10 plus t dt, and I'll insert the integration sign there and there. Hope that's okay. Right, the -2, I just took it up because it's constant. We know that's ln, right, pretty simply. We know in this case that is also ln, right? 10 plus t, that's ln. The derivative is of the denominator is 1. That's already there, so I don't need to do anything. That's just ln 10 plus t plus a constant. That's nice, actually, nicer than the previous one. Nicer numbers, right? Let's see what we got here. So I need something to help. There it is, right? Initial salt, right? Initial amount of salt used. So when t equals 0, q equals to 20 kilos. Yeah, sub that in. So you got ln 20 equals to -2 ln 10 plus c, right? So so you can combine it, right? So remember your log laws, right? Now, do I want to put the negative in? Yeah, why not? Same diff. So I'm just gonna, put the 2 up here, right? So I know that's ln 20 equals to minus ln 10 to the power 2 plus c, plus it over. Therefore, c equals to ln 20. That's 100, right? So ln 20 plus ln 100, so that's ln 2000. Is that right? ln 2000. Yeah, because I put it over. Cool. Let's sub that. Someone check the log laws for me. I hope he's right. Yeah, hope he's right. Sub that in. Well, I got ln 20. No, so not there. Don't sub it in there. Sub it into the expression up here. Right. Therefore, ln q, guys, everything's positive, right? So let's just forget about the absolute values. Minus 2 ln 10 plus t plus ln 200. Now, what do I want? I want q as a subject, right? Yeah, I want q as a subject. So before I do that, maybe combine all my ln's, right? Let's get rid of it, right? So it looks and feels like, yeah. What's this question saying? Solve, okay, solve. So they do want me to clean up. I was gonna say maybe I just sub it in, but yeah, let's just solve it. So ln q. So bring that power upstairs. So basically this becomes like -2 then. Right, and then plus means I time, so that's like ln 2000 over 10 plus t squared. Therefore, q equals to, because they're both logs, get rid of logs. Essentially like exponential both sides. Now, I don't know, can I just check a number? So let me just punch it. So I'm going to sub in 5, right? I think the question says after 5 minutes, find q. So far, I think that's right. Let me just check. I might have made a silly mistake. I don't know. Let me just check. I'm going to punch 2000. Put 15 squared on the bottom. Oh, no, sorry, perfect. Never doubt yourself, right? So once you get that, that is the expression, guys. Yeah, that is the expression. That will get you 2 marks, I'd say, in this question so far. Last but not least, the question says, after 5 minutes, find Q, right? So easy, right? Just sub in, oh, I'm at there. Oh, look at this, good planning. So when T equals 5, then Q equals to 2000 on sub 5 into that 15 squared. So equals to 80 on 9, I believe, which is 8.89 kilograms. Nice. I did it slightly differently to the James Risk solutions, which is why I sort of had to check, but that's how you do it. Guys, that is mixtures and solutions. One of the harder applications of the differential equations. We have logistical growth. Now we have this. You know, the easy ones are the normal exponential growth and decay, and also the modified. These ones are harder. I hope that was good, right? So if you like that video, please give me a like, tell your friends, make them subscribe so they can get the future updates that I give it. Differential equations, I'm going to leave that topic there. So when I see you guys next week, I will start a new topic. I won't announce it yet, but it's going to be a new one. Guys, thanks for that. See you guys later.